Boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with Helen Scales. Hello, Helen.
Hello.
And with me, Chris Smith. Now, in this week's show, new insights into dyslexia. Scientists have found differences in the brains of adult dyslexics compared with people who don't have dyslexia. Also, why the Sahara Desert could be bad for the world's oceans. It's allegedly producing copper-rich clouds of toxic dust that could be wiping out marine plants. And also, a new paint that will repair itself automatically when it gets scratched. You just trigger the process by going for a drive in the sunshine, which could be tricky in this country, but I'm sure there are plenty of places where that will pay off. We'll be hearing how it works in just a second. Helen.
Thanks, Chris. And this week we're taking you on a tour of the Cambridge Science Festival, which is on right now. We'll be hearing how far you'd have to cycle to burn off the energy in a single pizza. And trust me, the answer is really quite shocking. We'll also be hearing how mobile phones work and what the future holds for mobile technology. And our own Dr. Dave has been doing some electrifying demonstrations of his own.
OK, this is, in theory, quite a simple experiment. I've had to put some work into making it safe. Basically, I've got a gherkin here between two forks in this little box I've built. Well, now what I'm going to do is actually put mains electricity through this gherkin.
Simply shocking. But what's actually going to happen when Dave connects his gherkin up to the national grid? We'll be finding out in this week's Kitchen Science Strictly Not to Be Done at Home experiment in just a moment. Also on the way, bad science author Ben Goldacre will be here to tell us about lies, damn lies and statistics and how we're being deceived by dodgy maths. That's all coming up. If you'd like to get in touch with the programme, the email address is chris@thenakedscientist.com.
The Naked Scientist Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
This week, scientists have published in the journal Current Biology some very exciting work done on dyslexia. This is a common condition and it affects between 4 and 10% of adults in the Western world. And it's where people who have dyslexia have a problem reading, and they say that they struggle to read lines of text. They have no problem with language. It's actually when they come to read language that they get into difficulties. And for a long time, people have not really understood why this problem occurs, whether in some people it really exists or whether some people are using it as an excuse even. Some people have claimed that it's just an excuse for poor performance in some instances. But it certainly is a real entity, and the people who have it will certainly say they have certain difficulty. But what's actually going on inside the brain to make this occur? Well, this has been the subject of study of Vera Blau and her colleagues. She's a researcher at Maastricht University. And to find out, she recruited 26 people. Half of them, 13, were dyslexic and half of them were normal. And they put these people in the brain scanner and they gave them some simple tasks to do. And what they started off doing was just showing people pictures of letters. And while they were showing them the pictures of letters, they were scanning their brains to see which bits of the brain were lighting up when they were being presented with the pictures. Then what they did was to play people the sounds of those letters. So, in other words, the simplest sounds of language, they just played those sounds to people to see which bits of the brain were responding to those sounds. Then they made it more complicated. They started to pair the sounds and the pictures together. So, in other words, they did it congruously to start with. You would show someone a letter A, and then you would also play the sound A, or B, and B. And then they switched the task round and did it incongruously. So you would show someone a picture of the letter A, but then you would play them the sound B, for example. So the sounds and the letters didn't match. And a really striking difference emerged. People who have normal reading ability, they don't have dyslexia, when they were doing this task, whenever the sound and the letter matched up, they saw a very large amount of activity in a part of the brain called the superior temporal gyrus. This was not seen in the people who had dyslexia. And it was really astonishing. That's what Vera Blau said of the results. But why they say this is important is not only does it give us insights into where in the brain this is occurring, it also begins to give us insights into why dyslexia occurs. What they think is going on is that there's an integration in this part of the brain of the visual presentation of a piece of language and the sound. And what the brain does is to marry the two together, and when we read something, the brain decodes the appearance of the letters, and then you effectively speak it internally to yourself, hear yourself saying the words, and that's how you decode written language. And there's some kind of problem with this integration function in people who have dyslexia. And why this is an important discovery is that now we have some kind of objective readout of where in the brain it's happening. it might be possible to test various therapies designed to improve people who have dyslexia's ability to read and decode language, because you can test those therapies against these kinds of brain scans and see if they begin to make a difference.
Sounds like good news indeed for those people who are suffering from dyslexia. Well, I've got some rather bad news from the world of the oceans again, and that is that toxic chemicals in airborne dust that settle out onto the surface of the oceans could be disrupting marine ecosystems by poisoning the phytoplankton at the base of the food chains, which play a really vital role in regulating the global climate, and of course are also really important for those marine ecosystems all the way around the globe. And in particular, it's dust blowing off the Sahara Desert that's laced with copper, which seems to be killing off, or has the ability to kill off, some of the single-celled plants and algae, the phytoplankton, the tiny creatures that harness the sun's energy and absorb carbon dioxide from the atmosphere. Well, this was Adina Payton from the University of California at Santa Cruz in the US, who led a team of researchers, and they took air samples from different currents blowing across into the Red Sea, and they knew where those currents of air had come from. And sometimes it actually is beneficial to have dust blowing into the oceans from the land, because it can deliver vital nutrients, nitrogen and phosphorus, that are actually usually in short supply in the oceans. So that can actually fertilise the oceans, a bit like putting similar fertilisers on crops on land. But what they found was that some of the dust samples that they were mixing up in the laboratory with samples of seawater with phytoplankton in them, was that rather than stimulating growth, they were actually causing a sharp decline in various species of phytoplankton.
Suggesting there's something toxic in there.
Exactly, and so they had to think about what that might be, and they analysed these dust samples coming from different parts of the world, and found that in particular in the Saharan Desert samples of dust, it was copper that was very abundant, and we already suspected that might be the culprit because other studies have shown just how toxic copper can be to marine phytoplankton. But they tested it again, and they put copper at different concentrations into seawater and found there was a sort of dose-dependent response. The more copper you put in, the more of a problem you get with particular species of phytoplankton. And they think the copper's coming from the desert dust. About 65% of it actually comes naturally from the desert. So that's not really something that sort of mankind maybe is responsible for. But people do seem to be emitting around 30% from the combustion of various things in industrial processes. So we definitely are contributing to more copper in this dust that floats around in the atmosphere. These guys also put together a model of the globe to show where there might be other areas that are problematic, where we might be seeing this toxic effect of copper happening. And they've pinpointed places like the Southeast Asia and the Bay of Bengal, and these really could be areas where copper toxicity in the marine ecosystems could be a problem. One of the really worrying things is that it's not affecting all the phytoplankton. I guess it would be worrying if they were wiping all of them out, but it may well be that only certain species are particularly susceptible to copper. So what we might see is a shift in the type of phytoplankton living in the oceans, and that could trigger important knock-on effects through the rest of the ecosystem. So it's something that we might need to think about, what we're putting into the atmosphere and how that's affecting things living in the oceans.
It's amazing the effect the Sahara Desert can have on the world's weather and ocean temperatures. There was a paper published about a year ago where scientists showed an association between the amount of Saharan dust in the atmosphere and whether or not you had a bad hurricane that year, because the dust was blocking out sunlight, which warms the ocean, and when you get warm Atlantic waters, you're more likely to have hurricanes. So it's really interesting how this one body of material, obviously it's a huge body of material, but it can have big knock-on effects worldwide. It
is amazing. I've flown over the Sahara Desert, and it just goes on and on and on. It's an astonishing thing to see.
Thank you, Helen. Well, let's look also at the water, but also the question of whether you can make a sieve float, because Edward Lear famously sent the Jumblies to sea in a sieve and everyone said they would drown. But if they were in a sieve that had been treated by two Chinese researchers, Qin Min Pan and Min Wang, who are researchers at the Harbin Institute of Technology in China, maybe they wouldn't have drowned after all, because what these pair of researchers have managed to do is to turn sieves into waterproof boats. It's an astonishing piece of physics, but what they do is to take a meshwork, which it's a bit like chicken wire, but on a miniature scale, and you dip this in some cleansant, so you clean the surface so the metal is nice and polished and shiny. Then they treat it with silver, so you dip it into a silver solution and you get silver depositing on the surface, and then they treat it with a material called dodecanoic acid, which is sort of fatty acid. And when you put this sieve-like material in water, it just floats, and it will even hold a huge cargo. You can put lots of sand in little pots inside it, and it won't sink until, of course, you overwhelm the sides with water, and then it will sink. So it's working just like a boat. To find out why this works, they zoomed in with a very powerful microscope on the surface of the material, and you can see tiny dendrites, branches of silver on the surface, on all the bits of metal from the meshwork, and the silver dendrites give it a very big surface area to which this dodecanoic acid, which is fatty, sticks. So you then get this super hydrophobic, which means super water-hating surface, which coats the meshwork, and this traps a layer of air against the mesh because it hates water so much, and this means that the boat then repels water and it floats.
But we have boats that work quite well already, don't we? Why do we need to have sieves made into boats?
Well, they do point out that, yes, at the moment this is a bit ahead of its time. There's no immediate obvious application for this. But they say that you could see this being used in things like small underwater robots, in microfluidic devices, but also if you could scale it up to the big scale, because it traps a layer of air against the hull, if you like, then what you could do is use it to cut down drag enormously, because boats, when they're going through the water, obviously pull water onto the surface, and that creates resistance to the movement of the boat, and the boat has to burn more fuel to get through the water. If it was to ride on a cushion of air trapped by this substance, then this would save energy.
Excellent. Well, scientists have also this week discovered the missing link in the biological clocks of plants. You might think it's just animals and people who are able to detect light and with their eyes and respond to changes in the nighttime and daytime and respond to their behaviours accordingly. But plants can do it as well. And the mystery has been about just how plants are able to do this, because in the past, scientists have studied the plant equivalent of a laboratory mouse called Arabidopsis, and they've tracked down two primary feedback loops in the DNA. One that detects the onset of light in the morning, and a second that senses when light's fading in the evening. But what was missing was something to link those two together. But now Steve Kay and a team of researchers from the University of California in San Diego think they found that missing link, and it's a protein called CHE. Now, the presence of CHE has been predicted for nearly a decade, but it's only just now been found. And what the researchers did was they hunted around for proteins that bind to DNA and that switch genes on or off. And in particular, they were looking for proteins that change in abundance over time, because that really hints that they're actually involved somehow in the biological clocks. They're changing during the course of a day. Now, they found several cyclical proteins that do change in abundance, but it was only CHE that stuck to the region of the plant DNA that we already know is in charge of the ability to sense morning light levels. They took a closer look, and they also found that this same protein binds to the other part of the DNA that has this sensitivity to when it gets darker in the evening. So it could well be that CHE does seem to be this missing link between those two parts of the plant's DNA to be able to look at, to be able to sense when light's going up and when light's going down again.
Many people don't realise that plants have this body clock, and I actually spoke to one of the researchers that you mentioned there, Helen, about 2 or 3 months ago, and he told me that with a rising world population and climate change, we could be seeing plants having to accommodate living in different parts of the planet that they're not accustomed to, because different parts of the planet get different length days, therefore plants grow better at certain latitudes than others, and understanding these clock genes will enable us to get much more growth out of plants and therefore make them much more efficient.
Exactly. It's very important for plants to do things like time their flowering to be at the right time, so that it's not too cold and so there's lots of insects around and things like that. So there are lots of aspects of plant growth that are really tuned in to the time of the year as well as the time of the day.
Thank you, Helen. Well, also in the news this week, a new kind of material has surfaced. Ba-boom. This is the work of Professor Marek Urban, who's a researcher at the University of Southern Mississippi, and this material has the capacity to repair itself whenever it gets scratched. Sounds ideal for my car when I take a trip to the supermarket. Hello, Marek. Thank you for joining us on The Naked Scientist.
Well, thank you for having me.
Tell us how this material works.
Well, essentially, as you create a scratch on a plastic, and exposed to the sunlight, certain reactive molecules open up, and consequently they react with other species that are present in the system and form what we call crosslinks, and those crosslinks essentially seal the scratch that was mechanically created. So it's like a little silent species sitting inside of a system that is capable of self-repairing upon exposure to ultraviolet light. So
tell us what the actual chemicals are that you've used in the mixture, and how different are they from what we're currently using in paints and other surfaces?
Well, most of the automotive, for example, paints, and not only automotive but also floor coatings, utilize polyurethanes, which are fairly durable and fairly high-performance materials. However, they are not exempt from mechanical damage. And so what we created is essentially we took polyurethane network and also incorporated small amounts of chitosan. And chitosan is a derivative of chitin, which is the second largest carbohydrate present on Earth after cellulose, which was modified with the so-called oxetane. And that oxetane ring is one of those reactive sites that opens up as you make a mechanical scratch.
So chitosan is actually a derivative of chitin, as you say. That's the exoskeleton, the outer shell of things like crabs and lobsters, isn't it?
Exactly. I mean, and you have plenty of those things in the landfills along the coast of every country that deals with fishery and that sort of thing. As a matter of fact, a portion of this research was funded by the Mississippi Division of Marine Resources. So that chitin was, or chitosan I should say, was modified with oxetane, and that oxetane is a relatively easy to open ring. As mechanical scratch is created, that oxetane opens up, creating a reactive species, and that, upon exposure to UV light, creates another reactive species from chitosan, and those things react again to form a crossing network, therefore eliminating scratches.
So, to put it simply, you have the chitosan, which is this molecule, and you've coupled onto the side of it a ring structure, which, when the plastic or the paint surface gets scratched or damaged, that ring busts open. This makes it chemically reactive, and it can then grab either side of the damaged area and link it back together. Right,
exactly. So it's and the quantities of this material are relatively small. Therefore, although again this is the proof of concept at this stage, but we don't seem to see reasons why that shouldn't work in many other systems.
And just to finish off, Marek, when can we see this actually being used? Is there any reason why we can't expect to see this cropping up on car paints and car surfaces very, very soon?
Well, I think we should, and of course there are different types of polyurethanes being utilized in a variety of systems. Some of them are water-based, some of them are solvent-based. So it's slightly system-dependent, but those things can be worked out, and I really hope that consumer-driven markets like automotive markets and other, for that matter, will pick up on that and they'll take this seriously.
We'll have to leave it there. Thank you very much, Professor Marek Urban from the University of Southern Mississippi. He's got that published in the journal Science this week. You can read that if you want to find out a bit more about how it works. But basically, a very clever chemical structure based on a molecule you find in nature, in the shell of a lobster or a crab, for example, and it's activated by ultraviolet light. So if you get a scratch on your car, you go for a drive in the sun, and he tells me you need just 30 minutes in the sunshine, on a decent day, I presume, in order to make good any damage.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Helen Scales and Chris Smith.
Don't forget, we also beam this programme live into Second Life, and if you want to listen there, go into Second Life, go to the Scilands, and you just find The Naked Scientists. We've got a mansion there, and you should see all the other people listening to the show in their avatar form, at least, relaxing on one of our sun loungers. So do go and join them, and hello to all of you. We're watching you. Hello.
Today's show is all about the Cambridge Science Festival, and every year one of the big stars is our very own Dave Ansell, wowing the crowds with some great experiments. He also managed to find some time this week to do a bit of kitchen science.
For the Cambridge Science Festival Kitchen Science, I've come to meet Dave Ansell, of course. Now, Dave, you've got a really busy day today. You're doing lots and lots of talks, but you've managed to find time to show us something pretty cool.
OK, this is, in theory, quite a simple experiment. I've had to put some work into making it safe. Basically, I've got a gherkin here.
A pickled gherkin rather than a raw one?
Yeah, that's right. It's been pickled in vinegar and in salt.
Right. Not a big fan myself, but knowing you, we're not going to be eating them.
No, that's not what's going to be happening. I'm now going to put them between two forks in this little box I've built.
Now, these forks are quite badly bent round in a clear Perspex box with a lid, and they seem to be wired up to a big switch. What are we actually going to do?
Well, now what I'm going to do is actually put mains electricity through this gherkin.
So this is why you've had so much trouble making it safe?
Yes.
OK, now obviously you should never, ever play with mains electricity at home. Dave knows exactly what he's doing. He's built lots of safety precautions into this. And so later on in the show, Dave is going to pass mains electricity through two forks that go straight through a pickled gherkin. What do you think will happen at home? We'll be back later on in the show.
So passing mains electricity through a gherkin may seem a rather eccentric way to cook it, but Dave seems to have something other than food on his mind. What do you think is going to happen to the gherkin? If you have any clues, you can drop us a line. It's chris@thenakedscientist.com. Helen.
Now, if cooking gherkins with mains electricity isn't exactly your idea of a good meal, then there are plenty of other Science Festival activities all about the science of food. Mira went along to find out more.
Yes, I'm here in the biology zone at the Cambridge Science Festival, and there seems to be an emphasis this year on eating healthily and the importance of a healthy diet to have a healthy body. And with me is Gail Goldberg from the Human Nutrition Research Unit at the Medical Research Council. Now, Gail, your stand here is looking at the importance of a healthy diet, particularly for healthy bone. So firstly, which components of the diet are important for having healthy bones?
Okay, well, a number of components are important. The ones that are particularly important are calcium and vitamin D. About 99% of the mineral in our skeleton is calcium. We're born with about 25 grams as a newborn baby. When we finish growing as an adult, we have over 1 kilo of bone mineral in our skeletons. Vitamin D is important because that's a key to helping calcium form healthy bones. Firstly, by making sure that we take up enough from our stomachs, and it also plays a role in helping to make sure that mineral goes into bone and stays there. We do get some vitamin D from a few foods, but most of the vitamin D that we have in our bodies comes because of the action of sunlight on our skin, which means we make the vitamin D that we need.
But what about calcium?
Particularly in countries like the UK, we get most of our calcium from dairy products, from milk, yogurts and cheese and so on. That's because traditionally we eat a lot of those foods, and the calcium that's in them is very easily absorbed by our bodies.
And so what are the health effects if we don't have enough calcium and vitamin D?
Well, a number of consequences. In children and young people, they might not grow as much as they should. Calcium is important in adulthood to make sure we've still got healthy functioning bones. In pregnant and breastfeeding women, because the developing baby gets its calcium from the mother. And in old age, calcium stays important, and one of the particular health consequences in old age is osteoporosis.
Now, another one of your stands over there seems to have an exercise bike that children are riding, so I think I'm just going to head over in that direction.
And exercise is important for bones as well.
What you want to do, estimate how much energy it takes to pump the water from the bottom of the tube to the top of the tube.
I'm in a section that is looking into energy and where it comes from, i.e. the fact that it comes from our food. So I'm here with Martin King. What's going on in this section?
Basically, we're demonstrating here how much energy we burn off in everyday tasks, for example, cycling.
And so in order to show this, you seem to have an exercise bike with a tall tube in front of it. What's going on here?
Basically, the idea is, as you bike, water is pumped from the bottom of a tube up to the top of the tube. We're getting participants to estimate how much energy in the form of Maltesers it takes to pump the water to the top of the tube. Estimates have varied from 10 to 500.
And what is the answer?
The answer, in fact, is actually one.
Only one Malteser?
That's right, only one Malteser, and this is shocking to most people.
Now, I've just seen a child on this bike, actually, cycling for quite a while.
The average time it takes is about 2 to 5 minutes, depending on the child. Another interesting fact is that you have to pump the water up the tube 50 times to burn off the energy found in a typical pizza.
So you say the children have been cycling for about 2 to 5 minutes. So say the average was about 3 minutes, and they have to do that 50 times. That's 150 minutes. That's over 2 hours of exercise on this bike just to burn off a pizza.
Yes, this is neglecting the fact that we all have what we call a basal metabolic rate, basically the energy that you use without doing any work. So this doesn't take into account that.
So I've learned the importance of eating healthily for the strength of our bones, as well as just how much exercise we need to do to burn off something as small as one Malteser. So now I'm off to learn how to actually make healthy meals at the Sizzling Science lecture. So I'm now here with Dr. Susan Jebb from the Medical Research Council, who's been leading today's Sizzling Science talk and explaining some of the science behind cooking. Hello, Susan.
Hello there.
So what have you mainly been talking about in today's lecture?
We've been trying to show people that science is all around us in everything we do, and that cooking, there's a huge amount of science in there as well. And of course, we've also been trying to give people some important messages about how the food we eat really can impact on our health.
And so how have you been getting the science of cooking across today?
Well, we've had a couple of little tricks of the trade. We've been using a water bath to cook the meat in, because in that way we can hold the meat at a very particular temperature. Because if you cook meat at a higher temperature, actually you begin to break down some of the muscle fibres, and you really lose the texture. So a water bath allows us to control the temperature far, far better than you could in a conventional oven.
Now, during today's talk, you were mentioning about the glycemic index. So what is this, and why is it important for people to understand a bit about this when it comes to their diet?
The glycemic index is a measure of how rapidly the energy in food is absorbed into the bloodstream. Some of the research suggests that people who tend to choose foods with a lower glycemic index, meaning the energy is released very slowly, have a reduced risk of developing things like diabetes and heart disease.
Now, you also mentioned that if people don't necessarily have access to fresh vegetables all of the time, it's good to keep some frozen vegetables in the home just as a backup. So are these still just as good for you as fresh vegetables?
Frozen veg are a fantastic alternative to fresh. These days they're picked and frozen so very, very quickly. It really preserves all the nutritional value. Some veg don't freeze as well as others, and so the texture is sometimes not quite as good. But some vegetables, like peas, like sweet corn, even to some extent green beans, freeze really well. So they actually make for a very cheap and convenient option.
And what would you say the emphasis of today's sizzling science is?
I really want people to see food as something which is incredibly interesting, important, and a really valuable bit of their lives. And I think if they value food, they start to think a little bit more about what they're consuming, and that can only be good for health.
I can't quite believe, can you believe, over 2 hours of cycling for a pizza? I think I might think again next time I'm going to call out for a takeaway pizza.
It's all right on a motorbike, though, isn't it?
Oh, true. That's true. I don't think it works that way, does it, Chris? Anyway, that was Dr. Susan Jebb from the Medical Research Council. We're talking to Almira Sinthillingham. And before that, we heard from Martin King, a PhD student with the MRC, and Gail Goldberg from MRC's Human Nutrition Research Unit.
Thank you, Helen. This is The Naked Scientist with Chris Smith and Helen Scales, and we're celebrating the Cambridge Science Festival, coordinated by Cambridge University this week. In a second, we'll be hearing from Dr. Ben Goldacre from The Guardian's Bad Science column about how there are uses and abuses of numbers, and how people who don't comprehend risk get fooled into maybe parting with money for things that they don't want to buy, or taking pills to have health benefits that might be vanishingly small. That's coming up. First, here's an email from Evan Haynes, who kindly wrote to us and said, "Recently, me and the rest of my year 10, received our first GCSE results, incidentally for science, and now for the last few months I've been avidly listening to your shows and your podcasts, and as it happens I received the best results in my class, 3 A stars. I only got 3 questions wrong throughout all these tests, and because I'm in the additional science group, consequently I was the best in my year. So thank you very much for keeping my interest in science, Naked Scientists, and thanks for contributing to my success so far." So thank you very much for that, Evan. If you'd like to get in touch with us here at The Naked Scientist, the email address is chris@thenakedscientist.com.
Lifting the lab coat on the world's best science. The Naked Scientists.
And now, on The Naked Scientists, with me, Chris Smith, and with Helen Scales, we're going to talk to Dr. Ben Goldacre from The Guardian's Bad Science column to find out about the uses and abuses of numbers. Ben, thank you for joining us. Great to have you with us on the show.
Hey, hi.
Now, tell us a bit about what you're going to be talking about, because you're actually joining us here at the festival to give a talk a bit about some of these things. So what are you going to cover in your talk?
You know, you just reminded me I need to write one. I am going to write about the various different ways that people who really should know better make mistakes with statistics. So not the kind of easy ways that everyday people are fooled, but people in kind of senior roles in government, medicine and industry and the media and that kind of stuff.
Well, we've heard the phrase lies, damn lies and statistics. This is not a new phenomenon, so there must be some fantastic examples that you can showcase your talk with.
Yeah, and the interesting thing is actually that the same problems keep coming up time and time again. So, for example, screening is a very interesting issue. People are often, I think partly because it's attractive to think, well, surely doing something is better than nothing, to imagine that screening could be a useful way of firstly, detecting breast cancer in people where breast cancer is very rare, so outside of the current screening window of women over 55, but also perhaps screening, as MI5 suggested recently, everybody's computerised communication records to try and spot terrorists, or screening everybody for AIDS. And the interesting thing is, when you're trying to screen for something that's very rare, like being a terrorist or having AIDS, actually your false positives start to outweigh your true positives, even if your test is very, very good.
Let's just define that. So false positives, of course, being people that you accuse of being a terrorist and in fact they're completely innocent.
That's right. So it works best with a concrete example. If we take AIDS, let's say we've got a really, really brilliant blood test for HIV, and it will only give you a false positive in somebody who actually doesn't have HIV, one test out of every 10,000 that you do. Now, that's a very good test if you're doing your HIV tests on a population where people are fairly likely to be HIV positive. Let's say injecting drug users or perhaps gay men with a long history of unprotected sex. You might say that if the risk in that population is 1 in 100 and your risk of a false positive with each test is 1 in 10,000, then in general, if you get a positive HIV test in someone like that, then it probably means that they really do have HIV. But then if you do the same test on members of the general population who have a very low risk of having HIV, let's say, for example, general population in Britain, your risk of having HIV is probably about 1 in 10,000. So if you're doing your test on a population where only 1 in 10,000 people have HIV, and your test gives you a false positive for 1 in every 10,000 tests that you do, then actually a positive blood test is only going to mean that the person genuinely has HIV half the time.
So what should we do about this? How should this alter our practice? What should we do to make sure that we don't end up pursuing false leads statistically like that?
Well, I guess what it really means is you have to be very cautious about where you employ screening, and whether you think it's a good idea or a bad idea depends on the maths of individual cases. So just recently, the ex-head of MI5 wrote a report for, I think, IPPR saying, and it got a lot of press coverage, saying, well, you know, maybe we have to accept that the security services should have access to everybody's computerised records, so everybody's text message communication patterns, the lists of who they phone, access to the contents of their emails, their tax records, or their travel records, all of this stuff, because then we can use pattern spotting software to try and identify who is a possible terrorist suspect and who isn't. And that sounds superficially quite appealing. I mean, you know, you could make a case, if it was true that that was likely to spot terrorists, you could make a case. You could say, well, maybe it's worth sacrificing our civil liberties, it's worth sacrificing our privacy in order to catch terrorists. Now, that's a separate argument, that's a moral argument. But before you even get there, you have to be clear on whether screening is actually capable of spotting terrorists in the general population.
I mean, that's one of the criteria for screening, isn't it? We say when we're screening for something, if we can't actually detect it effectively or do anything about what we find, we just don't screen for it.
Absolutely. So there are two problems with screening for terrorists. One is terrorism is extremely rare. So there are probably, you know, at most you'd say maybe sort of 10,000 sort of likely terrorist suspects in the UK waiting to do something. And in reality, it's probably much, much lower than that. But then you've got to think, well, what's your test for spotting a terrorist? Now, our tests for spotting HIV in blood are really, really, really good. They're only wrong one time in every 10,000, which means they're right 9,999 times out of 10,000. That's an amazingly good test, and that still falls over when you're looking at something very, very rare. But your test for spotting whether somebody's a terrorist from looking at their telephone records are going to be much less accurate than that. They're going to be much less accurate in the two important ways that a test can be flawed. First of all, they're going to be quite likely to miss true terrorist suspects, but they're also going to be quite likely to falsely identify people as terrorist suspects when they're actually not. And if you run the maths through, you can see that even a test that's sort of 99% perfect, which is unimaginably good, will still identify thousands and tens of thousands of people as suspects, which is basically useless. It's worse than old-fashioned sort of tradecraft and investigation techniques, because what are you going to do with 10,000 possible suspects? You know, to try and investigate all of those people in any detail is obviously impractical.
I think people who cast their mind back about 10, 15 years will remember something called the Cleveland child abuse scandal, which was precisely this, wasn't it? It was a flawed test which basically caught just as many people who were innocent as it did guilty, and led to lots of people being accused of child abuse and having been abused who hadn't.
Is that right? I know nothing about that, I'm afraid. Sorry.
Well, it was a major issue with people applying a test which was very, very, very flawed in the sense that it was pulling out cases which some of whom had been abused, but many hadn't, and it led to great amounts of heartache, and it was major headlines for that very reason, for the reasons you've outlined, which is it's very difficult to be specific and accurate with these kind of tests. So let's sort of wind this up by you telling us then what you'd like to see done about this.
Well, I guess, I mean, a lot of the time, discourse on screening is driven by politics and emotion. So, for example, politicians will want to say, well, we're doing something really useful about breast cancer or heart attacks or stroke or whatever. We're having a big screening programme, and that feels like a really positive thing to do. And it's the same with sort of screening for terrorism. It's the same with screening for all kinds of things. But I think people do just have to be sort of rational about it and think through the figures. But, on the one hand, there's kind of what's the practical outcome that you want. But on the other, I actually am nerdy enough to think that the maths on screening is just really quite interesting in and of itself, and that's kind of good enough for me.
But you don't have to be a geek to go to Ben's talk, and he's on at the Cambridge Science Festival this week if you want to catch up with him. That was Dr. Ben Goldacre from The Guardian. He writes the column Bad Science, and if you are a bad scientist, then beware, because he'll be after you. Thanks, Ben.
You're listening to The Naked Scientist. Still to come, we will find out what happens when you hook up a gherkin to the mains electricity. Also, Diana O'Carroll will be here with the answer of this week's question of the week. But earlier this week, we sent her out and about at the festival to discover the science of mobile phones.
I've come to speak to Chris Cox here at the Cambridge Science Festival about the intimate workings of the mobile phone. So, Chris, when I make a call on my shiny new phone, what's happening?
OK, there's quite a lot of steps it has to go through. Basically, it all starts off when we speak into the microphone of a mobile phone, and that turns our speech into a nice electrical signal representing the sound. That all then gets digitised, converted into a stream of binary ones and zeros that represents the signal. The next step is it all gets compressed so that we all have to send fewer ones and zeros. Basically, that makes the whole process more efficient. Slight loss of sound quality, but it does mean that with lower data rates from each mobile phone, the base station can accommodate more mobile phones in each cell.
So how much is it compressed by?
Basically, it's typically down by a factor of 10 or so. The original signal is 64,000 bits every second, and it gets squashed to somewhere between 5,000 and 13,000.
So here's an example of me talking at 64,000 bits per second. Yeah, I'm on the underground. Yeah, can you put a pizza in the oven for me for when I get home? And here's an example of me talking at 5,000 bits per second. Yeah, I'm on the underground. Yeah, can you put a pizza in the oven for me for when I get home? So you can hear how the audio degrades, especially when you're not getting a very good signal. That gives you that in-the-shower effect. How is it possible to locate the last known position of a mobile phone? Because we hear about that a lot on the telly, maybe in Crime Watch, something like that. But how is it actually done?
Yes, that's quite an important technique, often for emergency calls, tracing crimes and stuff like that. The most common technique is basically by triangulation. If you've got a mobile phone sitting in the middle of, say, a triangle of 3 base stations, then the mobile phone can measure the time at which the different signals from the different base stations all arrive, and by comparing those times, it can work out exactly where it is and report the result back. Basically the same technique that seismologists use for locating earthquakes.
So there have been plans sort of floating around, lots of rumours, saying that they're going to put mobile phones on planes. Now, I don't know if I want to listen to someone saying, I'm on the plane, but if they do that, then how is it going to work?
Well, I must confess I'm not sure that I do either, but let's see how that will work. First of all, there's been a bit of a delay because they want to make absolutely certain that there's no interference with the electrical systems on board the aircraft. But once they have made absolutely sure of that, there's going to be a tiny little base station in the aeroplane itself, which will just be picking up signals from the 100 or so passengers on board, and then after picking up the signals, the aeroplane will send that thing down to a dedicated receiver on the ground, just by a point-to-point link that can handle a really high data rate.
We've had the 80s brick, and we've currently got shiny touchscreen, lovely phones that can do, well, what seems like just about everything. So what could possibly be next?
Well, there's a few different things. First of all, fairly similar to little receivers in aeroplanes, we're likely to be getting little base station receivers for our homes as well. So that is going to allow us to have all the capacity of a mobile phone base station that would normally be over a whole town for our own home, and that'll allow us to have really, really high data rates for really fast applications on our mobile devices in our home.
Would it be possible to share these base stations even if it's not your home base station? So if you're out and about, for example, you could get this high data rate from someone else's house?
You would need to sort out the billing arrangements for that, try and figure out whether it's you paying the bill or the other person owning the other thing paying the bill. So that is probably the next step down the road, but we'll probably get there eventually.
That was Dr. Chris Cox explaining how a mobile phone compresses the data so that Diana can order a pizza with very little bandwidth, and also how one day we could be phoning home from the skies.
And of course that was an event which was taking place as part of the Cambridge Science Festival this week from Cambridge University. Helen, you were actually at the Cambridge Science Festival because I snuck into the back of your talk yesterday on seahorses. I was very impressed and I was gobsmacked by the quality of the pictures you were showing. Can I just ask you a quick question about some of the stuff you showed, though? Because I was pretty amazed, because you said seahorses, some of them are 30 centimetres tall, down to some. There was one which was just, 7 millimetres tall, was it? The tiniest one?
17, I think.
17, so
yeah.
It's still just over a centimetre.
Yeah, just about a centimetre. It can sort of stretch across a...
But that tiny little seahorse was blending into corals and things beautifully, and can they change colour then?
They can, yes. That's one of the beautiful, magical, mysterious things about seahorses, that they change the colour of their skin. They don't have scales like most normal fish. They actually...
Helen scales.
Yes, not like me. Oh. They have a sort of an armour, body armour that covers their body, sort of overlapping plates made out of bone, and skin over the top of that, which they can change colour. And they do that with sort of spots, a bit dendritic spots of, a bit like ink really, and they can expand and contract, and so different colours kind of come through their skin, and they blend themselves really expertly. It's incredible just how amazingly well they can camouflage themselves.
Is it the same as seahorses and chameleons, how they do this?
Yeah,
these
I think so.
chromatophores, these cells with little pigment blobs in them?
Similar sort of things. And seahorses can also grow little outgrowths, and so some of them are sort of spotty, bulbous things to fit into their sea fan homes and look almost exactly the same. So they can grow costumes to suit wherever they're living. It's brilliant. Great thing.
Helen's got a book coming out later this year, and I will be buying a copy because it's a fantastic thing, these seahorses. They're just so elegant, aren't they? This is The Naked Scientist with Chris Smith and Helen Sculls. We're covering the Cambridge Science Festival this year, and coming up we'll be finding out what happens when you plug a gherkin into the mains. We'll also be finding out what happens when you molt, and in fact humans do, it turns out. But if you've got a question for us in the meantime, then chris@nakedscientist.com is our email address.
Laying the facts bare. I say. The Naked Scientists.
The Whipple Museum of the History of Science played an important host to a historic event this week, which was based on a booklet that was published over 100 years ago, and it was called Postprandial, that means having eaten something, Proceedings of the Cavendish Society. And this is basically where students and professors of physics would relax over a century ago and get together and sing some songs. And Ben Valsler went along to visit Dr. Jeff Hughes from the University of Manchester and was treated to a performance of some of those songs that hadn't actually been performed for more than 75 years.
In the dusty laboratory, mid the cobwebs and wax and twine, there the atoms in their glory ionize and recombine. Oh my darlings, oh my darlings, oh my darlings.
The postprandial proceedings of the Cavendish Physical Society were a collection of after-dinner songs that the research students sang at the annual Cavendish dinner every year. Some of the students were very, very good singers, and so they sang favourite songs of theirs. Some of them were very good aspiring lyricists, and they rewrote the words to some of the songs to reflect the events and personalities of the Cavendish laboratory. So they just told stories in their songs about what was going on in the lab.
This was a student thing. Was this just a lot of fun by the students and the young researchers, or did some of the more eminent people get involved as well?
Oh, at the annual dinner, the professor would be there, the head of the laboratory, and there would be guests who would have been usually former students of the laboratory who had gone on to jobs and scientific eminence elsewhere. But they'd be invited back, and that would create a very nice sense of tradition and continuity with the past for the current students. and the former laboratory members could be held up as role models for them as to what they might aspire to.
So a very good opportunity to meet really some of the era-defining physicists and scientists of the time, and at the same time have quite a lot of fun.
Absolutely. Can you imagine being in a dinner where you would see your head of department and a well-known Nobel Prize winner standing on their chairs, linked arms, singing Auld Lang Syne at the top of their voices? So that was very good for the research students and created a great deal of entertainment.
This sounds like a very casual thing. It happened at a yearly dinner, but how do we know about it? This sort of thing usually would be a bit of an inside joke that would pass by unnoticed.
This was a very serious informal tradition. The students were so pleased with their own songs that they kept them, and in 1904 they published them in a pamphlet, and that was republished in 6 editions up to 1926. So that's how we know about these songs, and we know something from diaries and letters and so on about how they were actually performed.
So could you give me an example of the sorts of lyrics that they were coming up with?
Yeah. A.A. Robb, the mathematical physicist, wrote this one about 1905, 1906, and it's to a sort of cod Irish jig called Father O'Flynn. And I like this one because I play the fiddle, and I play Irish jigs quite a lot. So imagine an Irish jig rhythm, and it's: of duns we can offer a charming variety, all the big pots of the Royal Society. Still there is no one of more notoriety than our Professor, the pride of us all. Here's a health to Professor J.J. May he hunt irons for many a day, and take observations and work out equations and find the relations which forces obey. When the professor has solved a new riddle or found a fresh fact, he's as fit as a fiddle. He goes to the tea room and sits in the middle and jokes about everything under the sun. Then if you try to look grave at his jest, you'll burst off the buttons which fasten your vest. For when he starts chaffing, though tea you be quaffing, you cannot help laughing, along with the rest.
Then isotopes of every kind grew morning, number, day. Dust and crust all he could find before the rest, and reading might of a sympathetic but days mankind, not casually and gaily. The roll of numbers.
And this evening we've seen some of them performed by the HBS choir. Do you think this might be the first time they've been performed in maybe 100 years?
As far as I know, this is the first time that the 3 songs that we've heard tonight have been performed since probably the 1930s.
So really quite a historic event that we've been involved in.
Absolutely. Historians of science these days are really interested in recreating historical experiments. What we've heard tonight is the recreation of historical songs, and I'm absolutely thrilled.
This there is no possible doubt, no probable possible shadow of doubt, no probable possible shadow of doubt, no possible doubt forever.
It was Dr. Jeff Hughes, who's the president of the British Society for the History of Science, and the HBS Chorus performing songs of the Cavendish Society, and that's the first time they've been performed since the 1930s. Helen.
Right, well, now it's time to go back to Diana O'Carroll, and she has been tearing out her hair this week over this week's Question of the Week.
This week, the spring season in fashion is all about fur.
Hello, my name is John. I live in Hong Kong, and my question is about molting. Do humans molt like other hairy animals, such as cats and dogs? In other words, does our hair get thicker in winter while we molt in the summer? And if we don't molt, did we once have this function, and have we since lost it through evolution?
So is this why I'm made to clear out the shower every week?
My name is Professor Des Tobin. I'm currently Associate Dean for Research in the School of Life Sciences at the University of Bradford. For most animals, like rodents, for example, you have a clear-cut wave of hair growth where all the follicles are synchronized. I mean, molting requires synchronicity in the follicles because the hair grows in a cycle of growth that we call anagen and kind of resorptive phase called catagen. In the human, there is quite a bit of synchronicity in the very early stages, before birth and in the neonatal phase, but it breaks up very quickly. so that you get what we call a mosaic form of hair growth, where each follicle kind of is an autonomous mini organ. And whilst to some extent that can be re-synchronized, for example, when women are pregnant because they change their hormonal stimulus. Some studies have been done way back on the hair on the thigh. I don't know why they chose thigh hair to check the seasonality of hair, but it was showing that in certain times of the year, perhaps a little bit related to weather, although for humans you have to be very careful because of the fact that we're wearing clothes for a very long time and we don't need it for the same thermoregulation that mammals would have. But there is some very minor kind of peaks. If you were to do hair counts, we tend to see more shedding as you go into the summer period than going into the winter period. Some people kind of sign it as a vestigial effect.
Head hair grows continuously, but thigh hair does do a bit of molting. So be sure to get those legs out if you want to show off your shiny new coat this summer. And on our forum, we had a lovely discussion about the seasonal sloughing of skin. So thanks to Emilia Romero and Dent's student for that. Next time, I'll be consuming orange foods, all in the name of Question of the Week research.
Just as flamingos get their pink color from the pigmentation in the krill they eat, adult penguins get their yellow spot on the face from the same source. My question is, would there be any pigmentation changes in a human's hair or skin color if he or she ate plenty of raw krill?
Should the army be eating extra greens for camouflage? Let us know what you think the answer is by posting in our forum. That's the home of Naked Chat. It's at thenakedscientist.com/forum. You can also email us, and the address is chris@thenakedscientists.com.
Thanks, Diana. That was Diana O'Carroll with our Question of the Week, and she'll be back with more next week. But if you'd like to catch up with previous Questions of the Week, they're all available as a podcast, and you can find that on iTunes or at thenakedscientist.com/Question of the Week.
Well, earlier we left Ben and Dave preparing to pass 240 volts, that's mains electricity, through a pickled gherkin that they'd stuck on the end of two dinner forks. Here's what happened.
Welcome back to this week's Science Festival Kitchen Science. Again, there's lots going on today, and Dave has put a pickled gherkin on two bent forks in a special safety-conscious plastic box, and he's actually about to pass mains current through it. Now, Dave, I'm expecting an explosion, perhaps, or certainly nasty shorting out. I'm hoping that the lights won't go down. What do we expect is going to happen? Before we actually switch this on, what do you expect?
Well, gherkin will conduct electricity. It's got lots of salt in it, and salty water is quite a good conductor, but not a very good conductor, so there's going to be quite a lot of resistance there, so it should get very hot.
OK, so just like passing it through the wire in a light bulb, it'll resist and it'll get hot.
Yeah, and then something else even more cool should happen later.
OK, so we're going to plug this into the mains now. We'll close the lid to make sure that it's safe. And Dave, you have a special box here to make sure that we actually arm it so it can't go off by accident.
Yep, so I'll turn it on and then I just push this button and it should put live mains through this gherkin.
OK, let's see what happens. Well, the box is filled with smoke or perhaps steam very quickly. In fact, I can't see the gherkin anymore. But actually, the noise you could hear there was the gherkin not just sparking, but glowing. It glowed orange.
Yeah, the first thing that happened was the gherkin got very hot, and it got so hot that the water in the gherkin started to boil, and it filled the box with a cloud of steam. Then this dried out the gherkin around the prongs of the fork until eventually you get a gap with no water in it, so it doesn't conduct electricity.
Was this why we saw sparks then near the prongs, because the electricity has to jump through this gap?
That's right, it's now insulating. The electricity still wants to pass over that gap, so it starts to jump, forming little sparks. But the sparks weren't blue, they were actually yellow, weren't they?
Yes, they did look yellow, and even more than that, the whole thing seemed to glow. This wasn't just light coming from individual little sparks. The whole thing took on a colour, almost like a light bulb.
It was actually light coming from individual sparks, but because the gherkin was pickled with salt, sodium chloride, there's lots of sodium in there. And when you give sodium lots and lots of energy, like if you put it in a flame test you may have done at school, it glows really bright orange very, very efficiently.
And it's sodium that we use in streetlights as well, which is why you get the orange glow from a streetlight.
Yeah, that's right. The reason why they use sodium in streetlights is it emits light incredibly efficiently. So the little sparks inside on these forks emit light very, very efficiently, so well that the whole gherkin starts to glow, and it glows orange.
So why orange?
Well, inside a sodium atom, the electrons can only be at certain energies, and so they can jump up different steps. They can move up and down those steps by either absorbing light or emitting light. And different size steps give out different colours of light. And the only step which emits visible light, which we can see, produces orange light.
So it's to do with the levels of excitement of electrons in these sodium atoms. And because they can only be at certain levels, it can therefore only give out certain energies, which happens to come out as certain wavelengths of light, and that's why it's orange. But what if you'd pickled it in something else?
Something I have done in the past, but I won't do now, is pickle it in strontium chloride. And strontium, instead of giving out orange light, will give out a really bright red light. So you can get a bright red glowing onion, was what I did.
Fantastic. Well, I don't think these are going to be quite as efficient as streetlights themselves.
And they stink.
And the room does absolutely reek now of pickled gherkin. But the audience in here is filling up. You've got another fantastic talk to do. What are you doing your talks about today?
Well, this morning I did several on gases and liquid nitrogen, and this afternoon I'm doing a load of talks about electricity and sparks. So this will be centre stage in one of my talks this afternoon.
Fantastic. Well, thanks ever so much, Dave. That's all we have for this week's Kitchen Science. As always, there's loads more experiments you can do on the website at thenakedscientist.com/kitchen science, and we'll be back next week.
Ben Valsler with our own Dave Ansell. They were electrocuting a gherkin, and the reason it glows orange is because the sodium which is in the gherkin, that actually glows an orange colour when you put energy into sodium atoms. And it's exactly the same thing that happens with a street lamp. So Dave was making a miniature version of his own street lamp, effectively.
So could we put gherkins in our street lamps? That's the question.
Wouldn't be very bright and a lot of smoke and very smelly.
That'd be a bit smelly, yeah, absolutely.
But it could work.
It could work. We've had a phone call from Keith, and he wants to know how is it that homing pigeons find their way home?
Yeah, it's been a area of intense research in recent years, actually, and it turns out that pigeons and a number of other species, including bats, have metal deposits in their heads, and these metal deposits, hematite, they're iron, and they're magnetically sensitive, and they use the Earth's magnetic field as a kind of compass. And so what they do, they know that the sun rises in the east and sets in the west, and so by using sunrise and sunset, they are able to gain a timing, and they set their compass according to where the sun is at certain times, so they know what's east, west, and that gives them their compass directions. And so by changing their orientation relative to the Earth's magnetic field, they're able to navigate. And so they use this as a broad directional cue, and at the same time they also use visual cues because they have a hippocampus, part of their brain, which registers where they are in relation to their environment, so they remember visual landmarks and marry those together so they know where they're going and how they get home.
Hippocampus, which is named after seahorses. We also heard from Jane in Norwich, and she wants to know, can you actually completely get rid of MRSA, even if it's got into the lungs?
Yes, MRSA, methicillin-resistant Staphylococcus aureus. This is one of the hospital superbugs that we hear talked about. It's a very resistant bacterium, but there are antibiotics, including one called vancomycin, which can destroy it. And it tends to colonise lots of people. Probably about 10% of people might carry MRSA. It's increasing the amount of carriage out in the community now. But what we're finding is that if people do get it, then it can be cured by a big dose of antibiotics, even if you've got it in places like the lungs. So no reason to panic too much.
There you go. Hope that answers your question, Jane. Thanks very much for getting in touch.
Well, I'm afraid we've run out of time, and thank you very much, Helen. And thank you also to our production team, Diana O'Carroll, Mira Sinthalingham, Tom Simpkins, Ben Valsler and Dave Ansell. Next week, we're going to be venturing into the world of computer science. We'll be finding out what the next generation of computers has in store for us, and also meeting the man who originally wrote the game Theme Park, but has now become a brain scientist to work out how the brain works out where we are in three-dimensional space. Join us if you can.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.